Okay, so I wanted to just go over the employee example a little bit more to make sure everyone sort of gets the point of what we're doing here. So in my client program here, I've declared an object of type hourly employee. And so what that means is that this object here, Arnold, has all of these member functions available to it. So get hours, set hours, give raise, print check, and then constructors. Not only that though, it also has the functions that are in the employee.h class available to it, right? So it's got get name, get SSN, change name, change SSN. And it also has a net pay data member because I made this protected. Okay. And really what I should do is I should make this private. No, wait, let me think. Yes, I should make this private, and I should have an accessor and mutator functions to modify the net pay data member. Okay, so if we go back to the client program, you'll see that we've got Arnold.getName. That is from the employee class, right? There's my getName function. I also have Arnold.printCheck. That is from the hourly employee class, printCheck. Okay, so I'm free to use the member functions from either the class itself or from its parent class or base class. Any questions about how that's all working? Okay, so I want to move on to sort of the next topic in inheritance, and that is talking about polymorphism. Okay. So a programming language is required to provide three things in order for it to be considered a object-oriented programming language. The first thing is encapsulation. Do we know what that is? What's encapsulation? Encapsulation is a word you should know. Apparently I don't spend enough time working on terminology. Maybe that's okay. But so encapsulation is just, I might as well read my definition that I have here, if I can find it. Rats. Okay, so encapsulation, the ability to restrict access to an object's internal properties. What is that? The private part of a class, exactly, yeah. So another way of saying it is the ability to hide a class's implementation. Okay, so that's basically, the way we do that in C++ is we make the data members of the class private. So that's encapsulation. Okay. The second requirement that a programming language has to provide in order to be considered object-oriented is inheritance. And the third is polymorphism, which is basically a description of how inheritance is implemented in a certain setting, which we're going to be talking a lot about right now. Okay, so loosely speaking, polymorphism can be defined as being able to have two different functions with the same name, and having the compiler be able to figure out which one it is you mean. Okay. Now usually when people talk about polymorphism, they mean it in a more limited sense. So, but let's talk about ways in which we could have two different functions with the same name. Okay. There's one way that we've been doing that all semester. What's that? Two different functions with the same name. They have different signatures, and that's called, what are we doing to the function when we do that? We're overloading it, right? Okay, so one way that we have different functions with the same name is overloading. Now, normally when you talk about polymorphism, people aren't going to consider that to be an example of polymorphism. Then you have these next two are going to require some additional explanations. You might have to just kind of take it on faith for a second until we get to it. But the second one, situation is if you have a base class and a derived class with the same name. Okay, and the compiler by default in C++ figures out as it's compiling the program which function to call. Okay, that again, that again is not what people are usually talking about when they say polymorphism. Okay, so the third situation is what we mean when we say polymorphism, and that is same thing. We have a function with the same name in the base class and the derived class, but the compiler doesn't decide which function to call until runtime, until as the program is running. Okay, so we're going to spend a lot of time I'm going to spend a lot of time trying to show you why that matters. Okay, so hang on to that part of it. But basically what's going to happen is, if you can imagine, just think for a minute about how the compiler is actually going to do that. Okay, basically what the compiler is going to have to do is it's going to have a table of different functions that have the same name, and it's going to have to generate code that says, okay, if something, then call this version of the function. If something else is true, then call it this other version. So it's going to have to generate code that decides at runtime which function is going to get called. Okay, so that's polymorphism. So other terms, just a little bit, since I need to focus more on terminology apparently. So when we do this third method that I just talked about, we call it late binding or runtime binding. So binding just means binding the function call to a particular function instance, right? So that's binding. And then just the opposite, if it's happening at compile time, we call it compile time binding or early binding. Okay, I forgot. I was going to set something up here. I think I'm done with employees, so I'm just going to close out of all of these. Okay. All right, so here's a program, and we're going to just study it for a couple minutes here to see if we can understand what's going on with it. I have 3 classes here. I could probably make that a little bigger. Okay, so I have a base class, and my base class just has one public member function named vfunc, and it just prints off, this is the basis vfunc. And then I've got this derived one class, which is derived from base, and it's exactly the same except it prints a different message, right? That's just so we can tell which function is being called. Is it the base class function that's being called, or is it the derived class function that's being called? Okay. So let me, just to make sure, this looks a little differently than how we usually do things. So don't let that like freak you out. Okay. We don't usually define number functions right in the class, but you can, and so that's what I'm doing here to just kind of keep things concise. We don't usually create classes that don't have any data members. Okay, that's also a little odd, but it's okay. We're just doing this to illustrate, one very narrow thing. So we're just putting as little code as we can up there. Oh boy. My Blackboard, I'm quit on the computer that I was watching it on, but I guess that still seems to be working here. So. Oh, okay. I guess I'll just let that go. All right. So. In our client code, what I have is I have a pointer to a base class object, and then I have an actual base class object, right? And then I have a derived class 1 object and a derived class 2 object, okay? So what I'm going to do is I'm going to set P is the pointer. I'm going to set it equal to the address of B, so now it points at B. And then I'm going to call vfunc, the vfunc data member using whatever it is that P is pointing at, right? Then I'm going to set P so it points at derived 1 and call that vfunc. And then I'm going to set P so that it points at D2 and call that vfunc. Okay? So what would you expect the output to be? Sorry? Okay, that's exactly right. That's what we'd expect, right? This is base vfunc, this is derived 1's vfunc, this is derived 2's vfunc. Okay? Not what we got, though. We got base class every time, right? Let's think about why that is. So, looking up here, when you get to this function call right here, and you're the compiler, do you know what kind of thing P is pointing at? The compiler has no way of figuring that out, right? I mean, if it was really smart in this particular very simple case, it could probably figure it out because it just did it right before, right? But in reality, there's no way that the compiler could always figure that out without actually, compiling the program and then running it to see. That's why if you're going to do compile time binding, it's always going to give you the base class function. Does that make sense? Compiler can't figure it out at compile time. So it just goes by how you declared the pointer. You declared the pointer to be a pointer at a base class object. Okay. By the way, I guess backing up a little bit, is that even okay? Can I say this is a pointer to a base class object and I'm giving it the address of a derived class object? Is that okay? It is okay because of the rule in C++ that we consider a derived class object to be a base class object, right? Okay, so you can do that, and you will often want to do that, but it would be really nice if if you could actually have the correct the function that you intuitively think should be getting called, have that one be the one that gets called, right? Here, so what we mean is we want to figure out at runtime which functions should get called. And in C++, the way you do that, and I think, no, never mind. Put the word virtual there. In front of where that function is declared in the base class, put the word virtual. And that means this is a virtual function, which means that it's not going to be bound to an actual function call until runtime. Okay? So I just put the word virtual there. Let's run it again. Okay? Okay. Say that again? Oh, yeah. Okay, so I'm not sure which part of it. And so I think the part about how to do it is easy. What it changes is instead of the compiler figuring out while it's compiling which function is going to get called, it waits until runtime, because at runtime it will be able to tell which function it is that ought to be called, because it'll know that down here it'll know that P is pointing at a derived class object, derived one object.
Oh, because it is a base class, it doesn't know which function to use.
Right. Well, if you don't put the word virtual there, then at compile time, there's no way to know which function to use. Right. So it always just uses so if you do it at compile time, it just looks at the type of P, and that's all it looks at. And the type of P is pointer to base class object. So if you do it at compile time, it's always just going to use the base class object. Or it's always just going to call the number function from the base class, I guess I should say. Okay. You put the word virtual there. That means postpone the decision about which function to call until the program is actually running, so that I can figure out which one it's actually supposed to be.
And that always goes in front of the base class.
Yes, in front of the base class number function. Yes. Okay? So that's called a virtual function. Okay, so any questions about that?
Are there any kind of performance implications for declaring a function virtual?
Yeah, it makes running it slightly slower.
Okay. But there's no way to override a derived class unless the base class has been declared virtual, is that right?
There's no way. Yeah, right. You can't do that when you're writing the derived class. It has to be done when you're writing the base class. Yeah. Okay. Go ahead.
So, is there any kind of standard, kind of best practices for declaring functions virtual or not?
And that's a great question. In general, when you're creating a class, you're probably going to know whether this class whether a particular function is ever going to be overridden in a derived class. In fact, you're probably going to have intentions about that. You're going to have some number of functions that you know are never going to be overridden. You're going to have some that have to be overridden. If somebody wants to, so if you want to use my base class, you have to override this particular function. So I'm going to make it virtual. Then there's others that might be overridden. So the best practice is put virtual there if it's likely to be overridden. In other programming languages, like for example Java, everything is automatically done late binding. You can't force it to do compile time binding because they said, well, you know, why would you ever want to do compile time binding? Well, really the only reason is in case you're really worried about every billionth of a second in some sort of a application that you're working on, right? So that's why in C++, you know, one of the foundational philosophies of C++ is we're going to provide all this object-oriented stuff, but we're still going to make it possible for the programmer to write code that's as efficient as possible. And Java doesn't have that. I guess you could call it a restriction. Or so, you know, some might argue, you know, unless you're really worried about runtime, just make everything virtual. Anything else before I go on? Basically what I'm going to do now is just show you a couple more situations in which it matters. Okay, so one situation in which it matters is when you have a pointer to a derived class object. Wait, you have a pointer to a pointer that's declared as a pointer to a base class object, but you make it actually point to a derived class object, right? The second example that I'm going to show you is basically the same thing, except instead of a pointer, I'm going to use a reference. Okay, and so actually, this might be actually be an interesting time to learn more about references too, or at least to get a little refresher. So let me exclude that. Add existing item. Okay, so here I've got the same three. Let me get rid of the virtual for now. So the only thing that's different here is the client program. Okay, the client program has one function named f, and the parameter for that function is a reference to a base class object. Okay, so then I declare my three things down here. I have a base class object, a derived 1 class object, and a derived 2 class object, and then I call f 3 times, once with B, once with D1, once with D2, and then I get to see which function is going to get called there, right? So the way I have it right now, what's the output going to be? Base, base, base. Base, 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 right? Okay, and then to fix that, put virtual here. Now it does what we think it should do. Okay. All right, the third situation is a little more tricky, and actually, as it turns out, probably more common. And that is, so listen carefully to this. This is kind of a convoluted sentence, but when a base class function calls a function that is defined in both the base class and the derived class. So the base class, you've got a base class function and it calls another function, but that function that it's calling exists both in the base class and in the derived class. Okay, so if you use early binding, it's always going to call the base class version of that function, when in fact really you probably wanted it to call the derived class function. Okay, so here is an example of that. Oops, or not. Oh, that's not good. Okay. All right, so let's see if we can make sense of this example. What we have here is a little pretend graphics program, okay? And so part of the hard part about, the potentially confusing part about this is you have to sort of suspend belief for a second and say, okay, this is a graphics program, but it doesn't actually do the graphics. It just prints a cout statement explaining what it would do if it was doing the graphics. Okay? So I have a base class here called figure, and I have a class named box, which is derived from the figure class. And I have a class named triangle, which is also derived from the figure class. So in my figure class, I have a constructor, and it says constructing a base class figure object. Then I have a function that says draw, drawing a base class figure object, and a class named erase, which says erasing a base class figure object. Okay. Now, neither of those two functions should actually ever get called, because when you're drawing something, you can't draw like something that might be a triangle or it might be a box, right? You have to know which one it is that you are drawing. Same with erasing. Okay. Then I have this function named center, which is supposed to take whatever the calling object is and redraw it in the center of the window. Okay. So here's my center function. The way that I center an object is I erase the object by calling erase, and then I draw the object by calling draw. Okay, now notice this is a base class function, and I'm providing it in the base class because it's going to be the same algorithm for any type of object that is derived from a figure object, right? It's always going to be just erase it and then redraw it. However, as you can probably guess, if I don't have virtual, what's going to happen is it's going to try to call the erase member function of the base class instead of calling the erase member function of the derived class. Okay? And the same with draw. So, everyone okay so far? This is kind of an involved thing. All right, so for my box, I've got a constructor, and I've got a draw, and I've got an erase. That's it. Same, and then it's going to be exactly the same with triangle. Okay? So then down here in my main function, I declare an object of type triangle. I draw it, and then I say, okay, now I'm going to call the center member function, and then I do. Okay, so ideally what we would like to say here is, now I'm erasing a triangle, and then now I'm drawing a triangle. That make sense? Because that's how we center a triangle. We erase it and then we draw it. So, let's get rid of virtual for now. So constructing a base class. But by the way, this is a good example of seeing the order in which the constructors are called too, right? Constructing a base class figure object, and now I'm constructing a derived class triangle object. Okay, drawing a derived class triangle object. That was from when I called x.draw right here, right? So it's this is the cout statement that came from. To draw a member function of the triangle class. Okay, and then the derived class triangle object is calling center. And so in my center function, I have the cout statement that says centering a drawing by first erasing it. And then it says erasing a base class figure object, which is not what I want, right? I want it to erase a triangle. And then I say, then drawing it at the center. And it says drawing a base class figure object, but I want it to draw a triangle. Make sense? If you're tracking with this, that's excellent, because I probably would be sitting there going, I'll just look at the code example later and figure it out. All right, so if I put virtual in front of these two, and try again. Now it says erasing a derived class triangle object and then drawing a derived class triangle object. Okay? Questions about any of that? Okay. Yeah.
Is draw in the base class a function in the base class?
Here's the base class draw function. So the question was, is draw a base class function? And there it is. Okay. But there's something a little odd about having it there, right?
I was wondering why in the class program it drew the triangle object correctly, but it did something called erase, called draw object in the base class.
When I called erase, it, let's do it again.
Or center, sorry.
That's because it was the triangle object that called it.
So right here, I say x.center. That's a triangle object that's calling the center function. So up here in my center function, I call erase. Because erase is a virtual function, I'm going to be calling the erase member function from the triangle class, right? And same thing with draw. Did that answer your question?
I guess have to look at the code.
Okay.
So if you erase the two virtuals and run it again, when you first call erase, or when you first call draw, it still says triangle one. I think that's what he was talking about.
Oh.
In your class program, you draw.
You mean this one right here?
Yeah. And there's also a draw in the center implementation, what we call center. And those draws are different because center is.
The first one works without the virtual.
Okay, so the first one is, the first one doesn't really have anything to do with the base class, right? X is a triangle object, and so I'm calling the draw member function from the triangle class.
Okay.
So in that case, the base class doesn't even come into the picture.
Okay. Thanks.
Okay. There is something a little odd here, though, and these two functions here, our intention is that they're never actually going to get called, right? So why do we even have them there? Well, one reason that we might want to have them there is because we want to make it so that any programmer who derives a class from our class has to provide that member function, right? So here we are, we're creating our base class, and one of the member functions of our base class is this center function. But this center function only works if the classes that are derived from this class actually have an erase function and a draw function, right? Otherwise we're stuck. So one reason for having these is that we wouldn't compile if we didn't have them, right? Wait, hold on a second. Let me think about that. No, that doesn't make sense. Never mind. I retract that. But we do want to have some way of forcing the derived class to implement certain member functions, right? And this illustrates that. The way that we can do that, okay, I'm winging it here, and sometimes that turns into a bad thing, but let's see how it goes, okay? The way to do that is by using what's called a pure virtual function. And all that means, when you say pure virtual function, all that means is that you're not even going to provide an implementation of that function in the base class, but all derived classes are required to provide an implementation of that function. Okay, and syntactically, the way you do that in C++ is after the function declaration here, you say equals 0. Secret code, right? Equals 0. And then we get rid of that. Done. Okay? What that means is I'm not going to provide a definition of this function, but if you derive a class from my class, you have to provide definitions of those functions. Let's try it.
Why do you do that? You don't feel like writing it?
Well, no, because I don't know what class might be derived from my figure class. It could be a hexagon class. It could be a trapezoid class, whatever, a circle class. So it just means that so I don't know how to implement those functions, right? Because I don't know what kind of figure it is that's actually going to get drawn here. That's left up to the programmer who's writing the derived class.
Seems like you're forcing that on the program.
You are.
That's what you have to try to memorize.
You ought to be able to do it yourself.
I just don't see why. I just don't see it as very.
Okay. Well, I can understand that. Not seeing it as very useful. It turns out that it is, so I'm going to try to convince you. Maybe not right now, but as we go along. And I'll show you another example in a bit. I think that'll become obvious. But the idea here is, think of this from the perspective of the person writing the figure class. Okay, I'm writing a class, and the class I'm writing is never actually going to be instantiated, right? I'm never going to actually declare objects of type figure. The only reason for this class is so that other people, other programmers, can derive their classes from this class, and it'll save those other programmers a bunch of work, because I've declared all of this stuff that works for any figure. Okay, and really that's the whole fundamental idea behind inheritance, right? I'm making it so that the programmers who are writing these classes don't have to create everything from scratch. They can use some of the stuff that got declared in the base class. This example may not illustrate that very well because there's not that much stuff that's getting provided, right? The only thing being provided is this center function. But in reality, when you do this, you're going to there's going to be just like there could be 100 number functions that are provided for you, and you just have to provide a couple things and make the whole thing work. Okay. But I am saying that, okay, here's a class. I think this class will be really useful if you want to derive your class from this class. But if you want to do that, you're going to have to give me a draw function and an erase function, or it's not going to work. Okay? You still didn't test it, right? After all that. Yeah, looks good. Okay. Any questions about any of that so far? Yeah.
I have a weird question. So, hypothetically, let's say you have functions that you want to be overridden by the GI classes, and you have a function like center that calls functions that have the same name, but you want it to call the base class version. But you still want those base class versions to be virtual. Would you make 4 functions then?
No, what you could do in that case is you could actually use the scope resolution operator to make it call the base class version. Does that make sense?
Yeah.
So the question was, what if you have this whole thing set up the way that I have it set up here, but then you run into a situation where you really do want the base class, a base class member function to call another base class member function. So you can force it to do that by using the scope resolution operator with the base class in front of it. Any other questions about any others? Okay, let's take a break. And my computer says it's 9:23, so we'll start up at about 9:33. All right, so basically what I have left is I just have this one example that's fairly huge. It's taken straight from the textbook, actually, so you can see it there. Basically, the idea here is that I have a class called game that is set up so that you can write your own class that implements a particular game, and you can derive a lot of the work involved in that from this base class called game. So I think it's interesting because it demonstrates several different categories of member functions. You'll see in a second. So I'm just going to go down from the top, I guess. Right here we've got, there's going to be a type. So I haven't actually ever done any Newman here, so I guess I should take a second to make sure everyone's with me on this. We're declaring a new type called who, and who, a variable of type who is going to be equal to one of 3 things. It's either going to be equal to human, or neutral, or computer. Okay? So that, for example, that's how we're going to keep track of whose turn it is. So we have a constructor which just sets move number equal to 0. We have a destructor. Let's look at, so the only data member we have is this move number data member. Okay, so any other data members, we're leaving it up to the derived class to create. All right, let's see what else we've got here. We have a public member function. This one should not be overridden, so that's kind of the first category of member functions, a member function that should not be overridden. It plays one game with the human player moving first, the computer second, and it uses a very complicated algorithm to select the computer moves. Okay, and the return value is the winner of the game. Okay, so far? All right, second category of functions. Here we have some virtual functions that may be overridden if you want them to do something different in your game, but they have a default behavior that's illustrated, that's implemented here. So the display this is indented wrong. The display message function is going to have a default behavior. I guess we'll have to go down. We'd have to go to the game.cpp to see what it actually does, right? So we can do that in a minute. Get user is going to have some sort of a default way of figuring out who the next user is. But you could override that in your derived class if you want to. Who moved last? Here's the default behavior. Okay, if move number is odd, return human, otherwise return computer. That's how you figure out who the last mover was. Anybody not familiar with the syntax here? Okay, so this is a what's it called? Shoot, it's called a. It's a tertiary operator, which means it has 3 operands. I'm not sure. Are you sure that's right?
No.
Okay. Something like that.
Most call it the tertiary operator.
Oh, that's
most
tertiary.
languages, because that's the only tertiary
Right. But it has a name. It's the maybe it's selection or something like that. Anyway, so basically, the first operand is a logical expression. Then the operator has 2 parts. There's a question mark and a colon. So the first operand goes in front of the question mark, the second operand goes between them, and the third operand goes after the colon. Basically, if this logical expression is true, you do the second operand. If it's false, you do the third operand. Okay, number of moves completed, return move number, which happens to be the only data member in this class. Who's the next mover? If it's even, the next mover is human. If it's odd, the next mover is computer. Figure out who the opposite of player is. Right? So if player is human, then the opposite is computer. Otherwise, the opposite is human. And who winning. Okay. So these are all defined in the implementation file somewhere. Okay. So far we have member functions that should not be overridden. We have member functions that can be or may be overridden. We have virtual functions that must be overridden. Okay, now these are interesting. In our example before, in the drawing program, we had 2 member functions that had to be overridden, right? And we decided to make them pure virtual functions because we never actually wanted those functions to get called. And that was a way to force the derived class programmer to override them. In this case, though, it says the overriding function should call the original when it finishes. So in other words, we have these 2 member functions, and there are certain things that we know they should do no matter what, but then there's also some other things that the derived class programmer is going to have to tell it to do. Okay, so for me, go ahead.
How do they call the original? What's the syntax of that?
So if we look at a derived, if we look in the implementation file of the derived class and see and look at the definition of the make move function. Okay, so you use the scope resolution operator to tell it to call the base class version of the make move function. Okay, so the make move function and that other function, whatever it was, in the derived class you're going to have some code that actually makes the move, but then you also, when you're done with that, have to call the base class version so that it can increment the move number. Okay, so that's, and then restart, similar situation. There might be some other stuff that has to happen when you restart, but along with all of that, you're always going to need to set the move number back to 0. Okay, that's the third category. So can't be overridden, may be overridden, must be overridden, but also needs to call the base class version of the function. Okay, and then you have just pure virtual functions, which means they have to be overridden and I'm not providing anything. So that's these guys. So you have to provide a clone function, a compute moves function. Okay, so that's the hard part, right? You have to compute all the possible moves that the next player can make. And that is in a queue of strings. That makes sense? So we are representing each move with a string, and the derived class has to create a queue of strings that represent all the different possible next moves. Display status, evaluate. Okay, so what that's going to do is you're going to have to write a function that somehow gives a point value to a move, whether it's a good move or a bad move or whatever. And the higher the number, the better the move is for the computer. Sounds hard, huh? We'll take a look eventually. Maybe not today, but eventually. And then if a way of checking to see if the game is over, and a way of checking to see if a move is legal. Okay. All right. This guy here, search levels. That's the this base class provides this fancy, complicated way of figuring out what the best next move is, and the way it does that is by actually simulating a certain number of moves ahead. And this is the constant that controls how many moves ahead it simulates. Here's the function that's actually going to do that. And then here's a function to make the computer move, and here's a function to make the human move. Let's look at the implementation of the base class. So we're not going to go into too much detail in that fancy algorithm, but you can take a look at it if you want to. So to play the game, remember that was one that should not be overridden, right? That was the only function that said don't override this one. Restart while the game is not over, display the status. If the last mover was the computer, then make the human move, else make the computer move. And then after you exit the while loop, display the status one more time and return whoever won. Okay, there's the ones that you can override. The display message, default version just prints out whatever message you sent it. Okay. Get the user move. That's kind of a typical way of doing it. So unless you have some sort of a special thing, then you can just use this version. Winning is So I guess what evaluate does is it actually tells you who's winning, right? So I guess it's actually evaluating the status. It's not evaluating moves, it's evaluating the status. So I said it slightly wrong before. Okay, so you have to provide, this is one you provide, right? Was this one that the derived class had to have? Evaluate. Yeah. Okay, so the derived class has to have some way of evaluating the current status to see who's ahead. And it gives it a point value, the bigger the point value. And I think what it is that if the I'll take a stab at it, and but this will be a theory, and we'll see if it's true or not. If it's above 0, that means the computer's winning. If it's below 0, that means the human's winning. What else do we have? Okay, here's the big fancy function they keep talking about. Eval with look ahead. Okay, so we're not going to go into too much detail here. But so it's going to return an int, and again, I think this is the same thing where positive values are good for the computer and negative values are good for the human. Okay, make computer move. That's where we're going to actually call the. So here we compute moves. That's getting us a whole list of all the different possible moves. Then what we're going to do is we're going to make a clone of our game and set it equal to future, and then we're going to make a move and we're going to evaluate the status with that move on it. Okay, so this is another part of this figuring out what the best move for the computer is. Okay, so you can use this class without understanding all of this stuff. That's the point, right? And then make human move is you ask the user to enter the move, and then if it's legal, you do it, right? Make move. Okay, so that's the implementation of the base class member functions. All right, so what we have here is an actual example of a class that's derived from there, which plays the Connect 4 game. Anybody know what Connect 4 is? Is it? What's that? Of course. Is that it's like 3D, right? You can go.
No.
It's not. It's 2D. Okay. So 4x4. Oh, you slide them down, but it's a 4x4 grid, and you.
It's probably like.
Oh, it's bigger, and then you have to connect 4. Okay, yeah, I got it. All right. Sorry. Just a little bit of a right. Just a little bit of a. Okay. Anyway, let's look at the header file first. Oh, what happened to my header file? Okay, so we're deriving it from the game class, setting how many rows and columns we have. So 6 rows, 7 columns. Is it always the same size, or anyway? Variable? Okay. Depends. So here's the member functions that are overridden from the base class. And then there's a helper function. And so our data members are going to be a 2D array that I assume is going to store, okay, of type who. So every element in this two-dimensional array is either going to be user or human, or sorry, human or computer or neutral, right? And presumably it's going to start off all neutral. How many columns have been used, and the most recent column. Okay, so here's our constructor. I was actually thinking that we were going to have to initialize the 2D array in our constructor. I'll think about that. Anyway, so our constructor first calls the game class default constructor. That actually doesn't have to be there because that's going to happen automatically, right? We all know that? Okay. And then we're going to call the restart function. Maybe restart, oh, that's probably what restart does, right? Is restart in here somewhere? Yeah. Restart probably, I'm guessing, initializes everything back to the default. Where'd it go? Restart. Fills everything up with neutral. And then calls the base class version of restart. Remember what that does? Sets move number back to 0, right? Okay, so I don't know how much detail to go into here. Compute moves is where you're creating a queue with all of the moves in it, each move represented by a string. So the way that we're doing that is, let's see what move strings is. Well, that would be back in the header. So we had an array of strings, one for each column. So does that get initialized in the restart?
It's right there, actually. That's why we were straight. There's straight.
Oh, okay. There's the move strings. Okay. So basically the moves is just a string that represents which column your move is in, right? That's all the different possible moves there are. So compute moves just goes through each one of those possible moves, and if the number of spaces used in that column is less than the number of rows, then you push that move or that column number into the queue. So when the first time you call it, it's going to be a queue with 7 items in it, right? 0, 1, 2, 3, 4, 5, and 6. All the different possible moves. All right. I think that I may leave the rest of this as an exercise. Although it's, sorry, if I'm having maybe a little too much fun with it, but so here's my evaluate function. So for each possible starting spot, calculate the value of the spot for a potential foreign row heading down left into the lower right. So normally this is in the range -3 to +3, but if a foreign row is found for the player, the result is 4 value, which is large enough to make the total answer larger than any evaluation that occurs without a foreign row. So anyway, here's some for loops to see. Basically, we're basing the evaluation number on how many in a row you will have if you put it there, right? So, any questions about this? The main thing to illustrate there is just the 4 different, I guess, sort of the strategy when you're making a base class, right? You've got 4 different possible situations of member functions, whether they're overridden or not, and it's just a good example of a lot of stuff that goes on when you're doing inheritance. So it'd be a good thing to take a look at in the book and kind of make sure you get it. Although you don't have to get the look-ahead algorithm. That's probably okay if you don't follow that. Any questions about any of this? All right, I think I'm done with inheritance, so I'm going to just call it a day, and we'll start in on our final topic of the semester on Wednesday.
Actually, one question.
Okay, go ahead.
In your base class, when you are let's see, let me pull up the book a little bit. When you define those functions right below them, do you still have to define them in your implementation?
These?
Yeah. Like, see how that, like, who last mover, it's defined right there.
Yeah.
Do you still have to define it in your implementation?
No. If you define it here, then you're done. You don't have to do it again in your implementation. Yeah. And whether that's a good idea or not, I basically in here we're saying that's not a good idea, right? Because the implementation should be something that the client doesn't see. So apparently the authors of our textbook
They just do it because it's like a little one line.
right, if it's just a little one-line thing, sometimes you just throw it in there. So. All right, I'll see you guys on Wednesday.